Good morning to everyone. I'm Ashwin Rajas from the Department of AIDS, and I'm currently in my final year. And our project is Generative Adversarial Networks, and my team members are Bagu Divyashri, Shutraya Gangadharan, and myself. Our team number is 80, and this project is done under the guidance of Dr. S. Sellakumar. So now let's get into the project. So our project introduces a very powerful GAN-powered system which revolutionizes how we generate and manipulate data. So we leverage state-of-the-art deep learning architectures and adversarial training networks, which excels in creating realistic and high-quality synthetic data. And it also bridges the gap between imagination and reality. So you might have experienced tailored data generation with our GAN systems advanced algorithm, seamless integration with existing frameworks, and intuitive control over output quality. So our approach signifies a significant leap forward in the field of generative modeling. So the statement of the problem. So in many machine learning tasks, the model requires a huge data set. If a data set contains an abundant data, only then the accuracy and the model would be trained in a very good manner. So in this domain, there always exists a challenge of generating realistic and diverse samples so that it can represent the underlying data distribution more accurately. So traditionally, these generative models have often struggled to produce high quality outputs with sufficient variation and fidelity. So this limit hinders all the progress in image generation, etc. So there's always a need for us to generate more data using generative adversarial networks, which can address these shortcomings. So the scope of a project is to enhance data generation, which utilizes GANs to generate synthetic data that closely resembles real data so that it could mitigate the challenge of limited or unavailable data. So it also improves the data augmentation, which with diverse and realistic samples, thereby enhancing model generalization and performance across various domains. So you can also create content using this generation. So many artists and creative potential are being unlocked by GANs because they always generate a visually appealing content, which pushes the boundary of AI-driven creativity. So there are certain domain-specific applications as well. These can be used in domains such as medical imaging, natural language processing, or even computer vision to generate data and aid in tasks like detecting anomaly or even text synthesis, etc. There are significant advancements in generative modeling, which would enable generative models to be used for a broader applications in AI and machine learning. So the methodology that we have used here is the first step of every project is data collection and pre-processing the data. So we need to identify relevant data sets which is required by the model and pre-process those data. Now the next step in a project which is very crucial is selection of appropriate model and architecture. So we chose GAN architecture. Example, we would have choose DC GAN or style GAN. And then we have designed how a generator and a discriminator works. The next thing is the training setup and hyperparameter tuning. We need to set up the training pipeline in PyTorch, and we need to define the functions like loss functions and then optimizers and learning rates. And next, we have to enhance the training stability and convergence. This is very crucial since we need to implement stability techniques so that it can mitigate common GAN issues, which includes collapse or even overfitting. Next, we need to evaluate and validate the model. So the metrics which we use in this evaluation and validation is inception score and FID for quantitative evaluation. And for qualitative evaluation, we use visual inspection. And then we compare the performance with baseline or state-of-the-art models. And the final end of the project is we need to deploy it and document each step. So we explore deployment options like integration, real time, or even batch generation. And then the document methodology, architecture, training, hyperparameters, and insights are very crucial, which tells uh, people how far how the project has been evolved stage by stage. So this is the basic architecture or the flow of a project. We generate there's a random input vector which is being loaded to a generator model. The generator sample is then sent to discriminator model, and the generator and discriminator uh, go on a recurrent loop so that it could give a very good binary classification whether it is a real image or a fake image. So this is the use case diagram, and these are the use case classes. And then what are the algorithms that we have used right here? So there are two models present in this, which is a generator and a discriminator. So the generator, we just give some fake data samples, and then we just map the noise vectors from a latent space to the generator network, and this keeps generating images frequently. And the discriminator, so what the discriminator does is we just train the discriminator so that it is able to identify between real and fake data samples. And this discriminator will just keep on providing the feedback to the generator. So the generator would learn from the feedback and then generate even more better images so that it won't be classified as a fake image. So the next part is the adversarial training. So we alternately train generator and discriminator. So it is basically in a minimax game. We just uh, train both generator and so that we could improve the sample realism. And then the loss functions, the discriminator and generator loss functions, which is basically binary cross entropy and Wasserstein loss, which will essentially guide the training. And then the training dynamics are like we just use training epochs with back propagation and those sorts. So these are the hardware and software selections which we have done. So the implementation, like I said, the scope of the project and the methodologies we use. First, we need to collect the data and pre-process it, and then we need to choose GAN architecture and all those things, and then we need to design the network and the generator discriminator vectors. I think we've already discussed this, and then we need to set up the training functions and those loss functions, and then we need to tune, and then we need to train and evaluate the model, and then we need to optimize the performance so that it could increase the stability and then mitigate more collapse. And then we need to document and report all the steps which we have taken, and it's a trial and error method. If we had tried a step and it had failed, we need to document why it had failed so that we could improve our next step forward. And then we need to deploy the project, and then this keeps on going, the feedback and iteration. So whatever feedback we just get from the model or from the user, we need to take in the feedback and iterate the model, and this keeps on happening in a loop. So this is a code segment. So yeah, over here we have trained the discriminator. This is the discriminator function. Over here we are just, I think you would understand. It's a very basic code, which it's a with a very little bit of tweaks here and there. And then this is the generator code. And then over here, this is where the actual code happens. We need to fit the data, and then we have to perform the iteration. This is where everything happens. So this is the output. So this is the original sample data we had given. So based on this, it will assign, it will just change the noise vectors and then the latent space. And then this would be the first generated image. As you can see, all the images as look like they have been morphed into some kind of fake images. And then after 100 iterations, you can see the image, like most of the images are almost morphed into a completely different person. And it's like a, what do you say? That's created an entirely new image right now. So after 1,000 iteration or even 10,000 iteration, you won't be able to distinguish between fake and real data. So those data can be used in a training model to effectively implement whatever machine learning models or AI models, whichever you want to perform. So this is the training loss between the discriminator and generator, which essentially shows how much uh, both of them converge at each point. So these are the real and fake scores. So the conclusion is that there are many advancements in GANs, and then we have showcased their effectiveness in tasks such as unsupervised representation learning, image generation, image to image translation. And then what are the challenges and opportunities from this project is that it offers very good promising capabilities and even challenges as mode collapse and hyperparameter sensitivity, and those kind of complexities always remain, but we can only mitigate them to a level that it won't affect the project. But these challenges only present opportunities for further research and improvement. So future directions is that future research directions could include many regularization techniques or even optimization strategies and even domain adaptation methods. So the scope of project scope can be is that we aim to contribute to the advancement of GANs research by implementing innovative techniques, and then we have also addressed limitations in this project, and then we have also explored very new applications, and then we have ultimately pushed the boundaries of GANs and AI-driven creativity. So what future work can be done is that we could improve the scalability and efficiency, since all the software requirements by the GANs are super draining and it consumes more GPU space. So in the future, there's many GPUs coming like the 50 RTX 50 series, which will be way faster for GANs to be trained. And then there'll be more advanced architectures like many GAN variants like style GAN 2 or big GAN. And there'll be even more, we could see there'll be more of domain specific applications where GANs are being used. We could see in the future because AI is such a booming field. And then transfer learning, we could just investigate this transfer learning and we can fine tune it accordingly. And then we need to consider ethical considerations, since this can be used to what you say to mitigate privacy issues or whatever data issues. And then in real world deployment, we could collaborate with data systems and real world applications, as well as we need to make sure that they are following those regulatory and security aspects as well. So these are the references that we have used for our project, which includes a very good professor, Ian Goodfellow, and then from Tero Keras, and then we have articles from Philip Isola. So these are the very good GANs articles that we have referred for our project, and we've implemented certain techniques and we've tweaked some fine tuning as well. So you could refer this as well. So yeah, that's it. Thank you for watching this video. Don't forget to like and subscribe. Thank you.